Well,
Plugging in.
I have it though. Oh, I've done it. Not
Here, right? All right. Good morning, everybody. I look back at that clock. They still haven't fixed it. Okay. All right. So, are there any of these that you'd like to see me work?
The last one.
The very last one, the first and the last. All right. So, all right. How many want to see the first one first? Okay. Let's look at the first one first. That seems like enough now. All right, an electron moves at 0.140 C, as shown in the figure. There are points A, B, C, D, 1.90 micrometers from the electron. And then find the magnitude of the magnetic field of this electron produces at point A, B, C, and D. I'm sure that's probably what they are. Okay, now. I guess the big confusion, or one of the big confusions, is what do they do when they say 0.14 C? What is that?
Speed of light.
That means 0.14 times the speed of light. Okay, so let me zoom this in. Okay, so we got an electron moving. Okay, and the velocity is equal to, your numbers may vary, 0.140 c, which means 0.140 times the speed of light. So v equals 140 times, and let's see, speed of light in your text. What number do they give for it in the text? I mean, I can all estimate it here. You plug in whatever they give you. Because mine isn't going to have enough significant figures. But you just need to see how to do the problem. So 10 times 10 to the 8th, and that's meters per second. So somebody multiply that and tell me what you get for the velocity of this thing. Should be 3 point something times 10 to the 7. Or maybe 4 point something times 10 to the 7. What'd y'all get? You're as good as I am. 4.2 times 10 to the 7? Okay, so the magnetic field, we have some constants here. It's mu naught over 4 pi. What goes next? We have a charge Q, velocity V, so what do we put? QV. QV sine theta. Divided by what? R squared. And then our direction is going to be our V hat cross R hat. And that v hat cross r hat is what actually contains that sine of theta in there. So when you look at these v hat cross r hat, because these vectors aren't perpendicular to each other necessarily, there will be a factor of sine of theta in there. So if we just take care of the sine of theta over here, then we don't have to worry about it here. So don't do both. Okay, just do one or the other. Either say that the sine of theta is in the cross product, or the sine of theta is in, just put the sine of theta here. Probably easier to do this way. So, all right, let's just put things down here. So this is what? 4 pi times 10 to the negative 7 divided by 4 pi. Q, charge of what? Electron. So 1.602 times 10 to the negative 19. The velocity here is 3 times 10 to the, 4.2 times 10 to the 7th. I'm suppressing all of these units. Now this one I have to be careful, this one I have to make sure that I did it right, because as it says that the distance from each of those points is 1.90 micrometers. So the distance to each of these points that we're going to be looking at, A, B, C, and D, B's back there, C's over here, B's back here, and D's back here. Okay? So the distance to each of those points is, I ran out of room on my little diagram because I messed up. But so 1.90 micrometers, we have to take that into account. Don't square a micro. Write it out, then square it. Because you get micro squared, which is 10 to the negative 12th. So 1.90 times 10 to the negative 6 squared. And I'm going to leave the factor of sine of theta off. I'm just going to say sine of theta over here. Okay? Sine of theta there. Because that's what's going to change in each of these points. That's what's going to change at each of those points. Everybody see that, right? That's what things going to change. All right, so somebody please multiply all this out and tell me what you get. Oh, by the way, be careful here. 4 pi times 10 to the negative 7 divided by 4 pi is 1 times 10 to the negative 7. If you put this on your calculator differently, then it won't work. Okay? Okay, what'd you get? Wake up, get your calculators out. Come on, come on, come on. Don't run on anymore. I can stand here all morning. You don't want to hear me start singing. Do.
1.86
Sounds good enough to me. Nobody else is awake? 1.86 times 10 to the negative 7. And this would be Teslas, and we're going to multiply by sine theta, just depending on what angle it is. Okay? So, at point A, what is the angle between the velocity and the radius? Velocity goes up that way. So, it's the angle between the velocity and the radius. Let me draw the little diagram down here. So we have here. Here's the velocity. This is point C over here. Point A is up here. And this is 60 degrees. Okay? What angle do I put in here? 30 degrees. Because it's the angle between the velocity and the radius. The radius is along this line here from your point, from your charge to your point. So that's your R. So you put 30 degrees in here. Multiply this out, and that's the number you put in. And you're going to do that in each of these cases. Okay? So, you all can hard to see.
is such a small amount of magnetic field common. Like a 10 to the negative 7 Tesla.
Well, the Earth's negative field is an order of 10 to the negative 4. And that's the Earth.
I had an MRI last week.
Well, that's 1 Tesla.
Yeah.
Okay, that's large.
That's big.
Yes.
I'm
Okay.
scared.
Yes. Don't be scared. All right, now the only other thing is that we want to find out the direction of it. The direction of it we find out with the cross product. The cross product between the v velocity vector and the r hat. Okay? So the r vector goes up this way. The v vector goes that way. So remember how we do our cross product. Your straight fingers go in the direction of the first vector so that when they turn, they're in the direction of the second vector. Your thumb is pointing in the direction of the magnetic field at this point up here. So what direction did we get with our thumb? Into the page. We got into the page with our thumb. Okay? Now if I put into paper here, oh, okay.
Because it's
Because the
negative.
negative charge is coming out of the paper. For some reason, mastering physics does not have spell check. Here we go. The field is 0. So, and then just do the same for the other 3. Do the same for the other 3. When you get back here to D, it'll be 0 because the sine of theta is 100. Is theta, you could say, is 180 degrees. That'll be 0. So in other words, currents don't make magnetic fields along their axis. The magnetic field spirals around the current, not along the axis. Okay? So that should be enough to get you through the first one. So let's take a look at the last one. Okay. So down here, the last one, 29. Okay, here's another one of those using those laws that talk about segments of current and things like that. So in other words, we're talking, what we want you to do, or at least what I want you to be able to do, is understand what the Biot-Savart law says, what it says for those individual things. Okay? Because in practice, when you need it, or if you need it, you will be integrating over those segments to find the magnetic field, you know, at points A and B for the whole string of wire, for the long wire here. But here we're just talking about this wire segment here, just that point, just that little tiny segment. And when they talk about a very small segment, you can go ahead and use that law to approximate what it is. I don't want you integrating over 1.10 millimeters compared to 14 centimeters and all that. I don't want you integrating that. If you try to set up an integral for this one, you're pulling your hair out. So what you want to do is you want to go ahead and use the Biot-Savart law. I'm going to be transferring this diagram onto the paper. So we have a current, 10 amps flowing along. And we're given a segment here at point D. Oh. Okay, so this is 1.10 millimeters. Current is 10 amps flowing this way. And we're given, once again, points in which we're trying to find what the magnetic field is. So here's point A, here's point B, and the geometry of this is 14.0 centimeters, and this distance is 5.00 centimeters. Okay.
1.10 is that little.
Millimeters, that's a little segment here. Okay? So the magnetic field contribution from that small segment, once again we have our mu naught over 4 pi. Notice how they that appears in a lot of the formulas here, and conveniently all the pi's and stuff cancel out by the way we defined our constant mu naught. Kind of cool, huh? All right, about the only easy thing about it. So then the next one is I dl And I'll go ahead and put a sine theta here. We're going to go ahead and take care of the sine theta there, where the theta is between the dl and the r hat and the r, divided by r squared. And then our vector, I'm going to go ahead and put dl hat cross r hat. Normally this would include the sine theta, but we're taking care of the magnitude first here. Okay? By the way, when you're given the formula on a test, it'll be in that fancy, dl vector cross r hat vector. And you just have to remember there's a sine theta in there. No. All right, so let's plug and show. So here once again, this is 1 times 10 to the negative 7th there. I'll just do that because just divide that out already. Okay, the current here is 10 amps. Now the problem is that we want all of these things to be in the units of meters. So we have to divide this one by 1,000. So this is 0.0011. We'll leave the sine of theta till later, and I guess I can leave the r hat till r squared till later. Okay, so I'm going to put r squared down here, and I'm going to put sine of theta over here. Okay, so when I multiply this out, wow, I'm going to get, what do I get when I just multiply this top part out here? So we can. Let's see, 10 to the negative 6, 7, 8, 9. So 1.1 times 10 to the negative 9? Okay. So 1.1 times 10 to the negative 9 multiplied by sine theta divided by r squared. So all we have to do now, and the only reason why I'm doing it this way is because we've got those multiple points to look at. And it's going to ask you for each point. Kind of see how Mastering Physics loves doing this kind of thing in 2 years. All right, so at point A, in this case I'll do at least 2 points because there's various things that changes when you go to that second point, okay, or point B. Point A, what's the value of r squared? Or what's the value of r? It's 5 centimeters. Okay? And the angle between the vector dl, which is this vector right here, and the r squared, or the r vector, which in this case is this way, this is my r hat. What's the angle between those two?
90.
90 degrees. Okay? Sine of 90 is, by the way?
1.
1. It's the other way. Sine of 90 is 1. So 141 times 10 to the negative 9 divided by 0.05 squared. So what did you get for this thing? Something times 10 to the negative 6? You're basically multiplying it by 20. Whoopsie. You're multiplying this by 400.
4.4 times 10 to the negative 7.
All right. I love this algebra. So 4.4 times 10 to the negative 7. All right, so let me put this into the. All right, I need some help here. All right, how do I put this in?
2 times.
Times like this?
Yeah. No.
Oh, at function 8?
Well, erase the x first.
Okay, and then shift 8. Okay, shift 8. Shift that?
Yeah.
Oh, okay, 10.
10.
And then I do my little
up
pad.
and 6.
Oh, a pad on the 6?
Or you can do that.
I can do that. All right, so that's okay, good. Now, which direction is it? Well, these currents are a little, this time it's a little bit easier because you've got a kind of a current going on here. It's a little bit easier than your charge. So you could take your dl cross r and do it that way. If you use dl cross r, dl goes in the direction of the current, R hat points in the direction of the point, and your thumb is pointing out of the page. Remember, that's the magnetic field over here at point A. You can also confirm this. By using our other right-hand rule for currents, how they produce magnetic fields. Since we do have a nice current here, just take your thumb pointing in the direction of the current. Notice at point A, it points what? Out of the page. So that's going to be the same in both cases here. So the direction is out. Okay, now for this one, it says point B. So now let's take a look at point B. Here. Now we have to be careful, because there's a tendency here to want to think that those sine and thetas are going to cancel out, but that's not the way it happens. That's not the way it happens. Okay, first of all, we have to calculate what the R is. Okay? Or we can calculate R squared. That's actually easier than calculating R. Because R squared is what we use in our formula. So R squared is 14 squared plus 5 squared. So, whoops, I put on a, no. Bad. I'm doing what I told you guys not to do. Sorry. R squared is 0.14 squared plus 0.05 squared. Is it 0.0221?
Yeah.
Okay. All right, for my sanity, can you take the square root of that thing?
1486.
Yeah, okay, that's not good. 148. Yeah. It's just a check for me because I know it has to be something over 14 centimeters. But since this number is rather small compared to this one, it's not going to affect it that much. Okay? But here's your R for this one. Here's your R for that one. Okay? And then the other thing that we need to do is we need to take this is the R hat vector for point 2. And this is my DL. We need to find out what this angle is. Specifically, we need to find out the sine of that angle. So, that angle is theta. We need the sine of it. So the sine of that angle theta is the opposite side, 5, divided by the hypotenuse. So it's 5 divided by, 0.05, do it in meters, divided by 0.1486. There. So we'll put this all together for point B. Okay, so that's 19.6 degrees? Or
19.6 degrees, yeah.
Oh, okay. But, yeah, okay, that's fine. So let's plug all this in. 1.1 times 10 to the negative 9. Okay, let me just do it this way. 0.1486 squared. And then multiply by the sine of what you say, 19 point what? Okay. So somebody multiply that out and tell me what you get. Okay. Really?
1.7 times 10 to the 7.
That sounds more like it. Why did I squawk at what 10 to the negative 6 value? What am I comparing it to? I'm comparing it to the value we got at point A. Because if we look at this, first of all, this is at 90 degrees. So this point here is where it's going to be the maximum magnetic field contribution from this little piece of current. Okay? since I've gone even farther away and the angle's smaller, then it should be less contribution. Less contribution at that point. Once again, by the way, you can do the DL cross R. So if you do the DL cross R, DL in this direction, cross R hat in that direction, thumbs pointed out of the page, that's the direction of the magnetic field. Yes?
Can you do one more time the right hand?
Sure.
The right hand rule?
Sure.
Or the-
I'm going to do it over here.
The first problem with the vector.
With A or V? With V?
With the first, yeah.
You mean this?
Yes.
Confuse everybody, but here we go. There you go.
Okay.
All right. Straight fingers in the direction of the velocity V. So that when you turn them, they're pointed to one of those 4 points. Which way is your thumb pointing?
Straight.
No. So that when you turn them, this doesn't work. Because when you turn your fingers, it's pointed into the page. So you have to look at where you got to turn when you're pointing your fingers. So you point your straight fingers this way. But there's plenty of ways to do that. The way you tell is by which way you got to turn them. I got to turn them so that they're pointing toward one of these 4 points. Okay? Here. This was I'll forget it. But anyway, you do this and I'll just view all the parts. Or just part E. Oh, point C. What's point C? 0. It's along the current, 0. Okay. I thought they were going to ask at point D. I'm thinking, oh my, you can't because the R is 0. I was trying to think if they were going to try to do something like that. Okay. Okay. All right. You ready to move on to the new and exciting stuff? Okay, demo time. So for the first part of the demo, I'm going to put it right here. This. You can kind of gather around if you want. If you're over there and can't see it. Can you focus on this?
Yeah,
Turn the light on.
I'm good.
Okay, we're good. I'll try to bring it over. So make sure this video gets up soon so everybody can see it. All right, so what I have here is I have a metal loop wire connected to a galvanometer. And so the galvanometer is going to measure the current in that wire. So if I have current flowing in the wire, then the needle is going to go back and forth. Okay. So now there's ways to push charges around using a magnetic field. If I have a moving charge, if I have charges that are moving, and they move in the presence of a magnetic field, then there will be a force on them, which will cause them to move, which will create current. Okay, so I can do this just by putting the magnet here, moving the wheel into the magnet. There you go. Whee! Look at that. See? Move the loop in a magnetic field, and if you can see the little needles going back and forth. If not, just watch on the video because that's, probably, it's good, right? You see this, right? Fantastic, right? Here it goes back and got it?
I think so.
So fine, okay. All right, so there you go. Okay, so now hopefully you can stop now. All right, now here's the other thing. If I move the magnet, if I don't move the loop, and instead I move the magnet, what do you think would happen? Same thing. Well, let's see.
No.
Nothing? Or the same thing? Oh, look, there it is. The same thing happens. The same thing happens. I still get current, but I'm not moving the loop. I don't have moving charges. The loop has plenty of plus and minus charges in it, but since I'm not moving it, those charges are not moving. So the question is, what's going on? Notice that whether I either move the magnet or move the loop, the same thing happens. And you think it should. Especially if you've heard of Einstein's theory of relativity, where there's no absolute motion. So it shouldn't matter which one of these things is moving. They're moving together, they're moving apart, so somehow the same physics should be read. So I get current either way. This is what we talk about electromagnetic induction. So, my simple explanation, or somewhat simple, you can go through this fancy thing in the book. What happens is we find out if we take a magnet and we move it toward a loop, I can generate a current in that loop. Now the thing is that the charges aren't moving in that loop, because I've not moved the loop itself. So there is, well, if the charges aren't moving, then a magnetic field isn't going to produce a force on it. What would produce a force on the charge that isn't moving? Just regular old charge, how do I produce a force on it if it isn't moving? I don't use a magnetic field to do it, I use something else.
Another charge.
Well, another charge. Talk about fields. I'd use the electric fields. If I have an electric field, that'll produce a force on a charge. It doesn't matter whether it's moving or not. Somehow, by moving this magnet, I am generating an electric field inside of this loop. And this is what we talk about electromagnetic induction. Okay. So somehow I've got a magnetic field in there and it's generating an electric field. Now there's one part of this demo here. Okay, so I'm going to go back over here. Just so you can have this video. And some of you might have seen this before. Got it? Got it?
Yeah.
Okay. All right, now, get this. Okay, now, I have a magnetic field in there. Once it stops moving, stop moving. Okay, now I have a magnetic field in there. And notice there's no current. So it's not just putting a magnetic field in a loop. That doesn't work. Doesn't work if I just put a magnetic field in there. But notice, while I'm either moving the magnetic field in or taking the magnetic field out, I get a current. I have to somehow change what's going on. If I make a change, that's going to induce an electric field. So we get to Faraday's law of induction. Faraday's law of induction. Faraday's law of induction says that the induced current, the induced voltage is EMF. Induced current would be that voltage divided by the resistance in your wire, is equal to minus the change in magnetic flux through that loop per unit time. The change in magnetic flux per unit time. I introduced to you the magnetic flux earlier when we talked about the Gauss's law for magnetism. We had the integral of B dot dA for a closed surface is 0. But we're not talking about a flux through a closed surface. We're talking about the flux through an area that's subtended by the loop in question. In this course, we will use flat areas mostly. Okay? There will be one time when I mess up the area for you. Okay? So if it's a flat loop, the simplest area to take is the flat surface area. Just take here. Okay? Okay. That's the area we're looking at. That's the area we're looking at for this. It's not closed. It's not closed, so you can get non-zero things. Remember that magnetic flux is just like electric flux. So the magnetic flux is the integral over the area of B dot dA. That's magnetic flux. For a uniform magnetic field, this would be B, A, and I want to be consistent with your book, cosine of phi, where phi is defined as being the angle between the magnetic field and the area vector.
So B is A hat or A carrot?
What the angle between
A.
the and A. So in this case up here, remember that the area vector points perpendicular to the plane of the area. So therefore the dA would be perpendicular. dA is like this. Okay? So if the magnetic field is coming to the right, the dA is coming to the right, that's a cosine. The other way to try to remember this is that if the magnetic field is head-on to the area, in other words, my area is like this, and we don't tell you an angle, just assume that that's all going through there, that the cosine is cosine 0, which is 1. Okay? Okay. Let's give an example. Okay? So I have a loop, radius 20 centimeters in a magnetic field which pointed into the page, increases from 2.4 Teslas to 7.0 Teslas in 5 seconds. Okay? And so we want to find the induced voltage around the loop. All right, the induced voltage around the loop. Okay, so there we go. The induced. I'm just going to worry about the magnitude for the moment. Take care of that minus sign a little bit later. So I want D to change with respect to time of the magnetic flux. The magnetic flux is B A cosine phi.
How about the negative sign?
We'll just take care of the magnitude for now. That's a whole. We'll take that. Okay. So the magnetic field is into the page. So here's it. Let me draw a little magnetic field is into the page. All right. So what we want to do is we want to see which one of those things is changing. Because if it's not changing, we can pull it out of the derivative. Everybody see that? If it's not changing, we can pull it out of the derivative. You don't need it. I mean, we need it, but it's not changing, so we can just pull it out. So is the magnetic field changing? Yes, it is. How about the area? Is it changing?
No.
No, it's not. So we can come out. How about the cosine of phi?
No.
No, that's not changing either. And in fact, in this case, the phi is 0. Okay? You'll get a lot of these like this, with this into the plane of the paper where you've drawn a circle on the plane of the paper. That cosine is 1. Cosine phi is 1. That factor is 1. It's all going through, maximum going through the loop. Okay? So in this case, we just, if the area, in the area, we can just calculate the area. It's staying the same. Is equal to pi times the radius squared. The radius is 0.2. Square that. So somebody please calculate the area. I think I was going to let you get away with that using your calculators.
0.1256.
Point what?
1256.
Sounds close enough? What's your name? Joseph. Okay, so if this is wrong, blame Joseph. All right, so what we do is then now we have the area, which is 0.1256 meters squared times d dt, dB dt. Since we're not told exactly how, I mean, if you're given a formula for b as a function of time, like with t-squares and fun stuff in it, you could actually plug it in and take a derivative. Okay? We're not here. We're just given, it goes from here to here in this, so we could just change the d's to what?
Delta.
Deltas, because we're just told this is average. So actually, we're looking for the average induced. Yeah? So this is 0.1256 multiplied by 7 minus 2.4 Teslas divided by 5.0 seconds. Somebody calculate this and tell me what you get. Yes?
Why are we doing delta?
Oh, because since we're given average values, we're actually looking for the average. So we can. Okay? If we're given a specific function, you want to obviously use ddt. What'd you get?
0.1156.
Yeah, sounds good. All right, units of this. All right, let's just say what the units are, and we can worry about how they would work out later. But that's an induced what? Voltage. That's an EMF, electromagnetic force. Remember, electromagnetic force is not force, it's a voltage. That's a voltage. That's a voltage induced. So 0.1156 volts. A thing about units, there is a unit for magnetic flux itself. There is a unit of magnetic flux itself. If we look at the simple formula for it, or for the uniform, We have B, A, cosine B. Cosine B has no units. The units of B are what? Teslas. Units of area are meters squared. Okay? This is oftentimes referred to as a Weber. I don't even know why. I don't even know who Weber was. But anyways, referred to as a Weber. Somebody's friend or something. And so if you have so many Webers per second, because if you take this flux and divide it by time, you get the units of volts.
What is the 3 equal sign thing again?
Just the same as.
Oh,
Okay. All right, here we go. Now, why did you use this guy's name anywhere? I know it's around. They don't give this guy credit. I can't believe it. We must give credit to where credit is due. Remember you had a question earlier about the direction? We're going to look at Lenz's law. Once you get used to this and doing these problems, it won't be too bad. But when you first do them, you're going to be spending a lot of time just to figure out what direction that current is going in. This is Lenz's law. It says, the induced current in a loop is in such a direction as to oppose the external change that caused it. We go back to our problem here. And we want to look at what direction the current in that loop is going to be. That's the reason why there's a minus sign on the Faraday's law. Because your loop is going to oppose the change in flux. And we have to be careful because it's opposing the change in flux. It doesn't oppose the flux itself, it opposes the change in the flux. It opposes the change in the flux. So, there are 4 questions you have to ask yourself. Okay? 4 questions you have to ask. And they're kind of yes or no questions. Okay? Or A or B questions, or one direction or another direction of questions. Okay, so they'll have 2 possible answers. 2 possible answers. And from that, you can figure out what is going on with the loop. What's going on with the loop. All right, so in this case here, let's take a look. The first question you ask is what is the direction of the, and I'll call it the external flux. And when I say external flux, I mean flux caused by other things, not the loop itself. Not the loop itself. So in other words, it's stuff we do. It's what we are doing. What direction is the flux that we put through that loop? It's into the page. So the question for our example here is in. So we'll put right number 1, into the page. And then we ask, is that flux increasing or decreasing? Is that flux increasing or decreasing? Well, in this case, okay, look, we see. Well, it's going from 2.4 to 7 Teslas with the magnetic field. So what's going on here? Is it increasing or decreasing? It's increasing. So the flux here is increasing. That's question number 2. The flux there is increasing. Question number 3 asks, so the first 2 questions are about what external factors are going on. That's the first 2 questions. The next 2 questions are going to be about what the loop has to do. First thing is, we want the direction of the loop's magnetic field to oppose it. And I will stress this again, change. Oppose the change. So if that magnetic field is increasing, then what direction of magnetic field will do the opposite? Will decrease it. Out of the page. So if I put my loop magnetic field out of the page, I'm going to fight us putting more X's. In other words, we are putting more X's into the page. The loop wants to put dots to fight us. Okay? So in this case, the magnetic field from the loop must be out of the page. And then finally, we ask ourselves the question, what direction of current of the current in the loop will create that magnetic field? So if I need a magnetic field out in my loop, take your thumb, point it out of the page, your fingers are going to curl around the current. So it goes what? Counterclockwise. So the final answer here is counterclockwise. All 4 of those questions. Yes?
For number 3, is it electric field or magnetic field?
Magnetic field. We are creating magnetic fields. Because magnetic fields fight magnetic fields. The electric field is what's created in the wire itself. But the sense of that electric field is going to create a current that's going to fight that change. Okay, so let's do an example. Let's just go for here. Okay. Say I have a long straight wire over here, okay, and I have a loop right here. Okay. So I have a constant current in the wire. What I'm going to do is I'm going to pull the loop this way. Pull the loop away from a wire. Pull the loop away from the wire. So I want to know what is the direction of the induced current in that loop. Direction of the induced current in the loop.
When you pull it.
When we pull it away from the wire. Now, a lot of these questions you have to kind of figure out, because of the little combination question. We first of all have to figure out what is the direction of the magnetic field produced by this wire. In other words, this wire is our external thing. It's doing the magnetic field. So the first thing we want to know is what is the magnetic field from the wire in the loop? What direction is that?
Into the page.
Into the page?
I mean, it depends where.
wire?
Well, the wire's right there. The loop's right there, the wire's right there. What direction is it? It's into the page. Okay, take your thumb, point it in the direction of the wire. When you get up to where the loop is, it's going into the page. If I do the loop on the other side, then it would be out of the page. So the first question is, this is into the page. Into the page. Okay? Second. Is that flux increasing or decreasing? It's doing what? It's decreasing because we're moving away from the wire that's creating it. Farther away I get from that wire, the less magnetic flux I'm going to have. So this is decreasing. Third question. In what direction does my loop need to produce a magnetic field in order to oppose that change? Okay, write down an answer. Commit yourself to an answer. Everybody commit themselves to an answer? Hey, write it down, write it down. You can do it. Well, there's only real two options here. There's only two. If you say something else, then. All right, how many of you said out? How many said in? What are we opposing?
The pulling.
We're opposing the, not charge, the change. The change. We're opposing the change in magnetic flux. We're losing flux. If you're losing flux, you want to put more. Loops do not like change. So since this flux is decreasing, the loop wants to put it back into the page. So you got to remember when it's decreasing, the loop is going to want to put it back. Okay? And then the fourth question is in what direction is the induced current around that? Induced. Put your thumb into the page where you need the magnetic field. And so it's going to be clockwise. Okay. Now in practice, what we do with this is we have coils not just with one turn, but we have multiple turns, many, many turns. And so if those turns are identical, then we can multiply the induced voltage by n, because we got flux going through each one, we got a voltage around each one. So therefore, for multiple turns, we say that the induced voltage is minus n, where n is the number of loops. Change in magnetic flux with respect to time. Now, by the way, if we're asked for what is the induced current inside of said loop, all we have to do that is, this is a voltage. All you do is say that the induced voltage, the induced current inside the loop is going to be the induced voltage divided by the resistance of the loop itself. All right, now, I want to take a look at something we can do here. If I have a magnetic field, so I've got a constant magnetic field here. Least constant enough for our purposes. And I have a number of loops inside this magnetic field. I'm trying to draw like a 3D perspective here. And what I do with this loop is I spin it. I start spinning it. I start spinning that loop. So let's see what happens here. Okay? So I've got in loops and I'm starting to spin this around. So what happens is I've got an induced voltage here, which is equal to minus, I'm not going to worry about the minus, let me just use the fine minus. Yeah, fine. Minus number of loops multiplied by change in magnetic flux divided by change in time. Now what I can do with this is, if I look at this as minus n multiplied by ddt of the magnetic flux, which is BA cosine phi. Now, is the magnetic field changing? No, it's not. Okay? What about the area? Is it changing?
Nope.
No, it's not changing either. Okay, that's fine. What about the angle? That's what's changing. The angle here is what's changing. Okay? So, if we spin this around at a constant rate, we can define an angular velocity for this thing, omega. So that's what we're doing. We're going to spin this around with some angular velocity, omega. And so we can say that our phi is equal to omega times t. Omega times t. See, this is perpendicular to the... I did. Okay. You're staring at me. All right, so let's put this in here. So the magnetic field and the area come out. So in dA, cool, huh? All right, ddt, it gets better. Cosine omega t. Okay. What's the derivative of cosine? Negative sign. So the negatives are going to cancel out here. And then we take the derivative of what's inside, which is what? Which is omega. Okay? So the derivative of what's inside is omega. And so we get that the induced EMF for a loop, number of loops in magnetic field B, A, spinning at an angular velocity omega. I'm going to write the sign of omega t over here. And I'll switch the factors around a little bit. Because there's a factor of omega here, I'll just write it over here. And look what happens. Now notice what I'm generating here. What kind of voltage is this? Because look, it's a voltage that varies with time. Sinusoidally, yes, mathematically. More commonly, what do we call this?
Alternating current?
That's your alternating voltage, which is going to produce an alternating current. This is how you generate AC. You can either spin the magnet, or you can spin the coils. Either way you do it, you can use steam power to spin your magnet or your coils, coal, whatever combustion engine you want to spin the coils, generate electricity. Do it. And you get this sinusoidal current and sinusoidal voltage coming out of this thing. me see if they say anything else about this in the text. Your book. Kill it. I'm sorry. Okay. So those are generated. Let me go over one more. Source of EMF that we talk about. I have a magnetic field into the page. And I pull this along with the velocity v. I have a length L and a magnetic field B. And what I want to do is I want to look at the voltage that's generated along that rod. The voltage generated along that rod. And this is what we call motional EMF. Motional EMF. But we've ran out of time. So we'll talk about this on Wednesday. And we'll go over some more examples with Lenz's law, Faraday's law,